I'll be introducing you to our first alumni, Satadal Sengupta sir. He's basically B.Tech CSE pass out from NIT Durgapur in batch 2013. Okay. So right now he's working as a fourth year PhD student in University of Princeton in Department of Computer Science and Engineering. Yeah. And you'll be delighted to know that he is under the guidance of Professor Jennifer Rexford, who's well known in the field as told by Sensor many times. So, and now I'll be focusing on his current studies. So he's currently, his current research aims at enabling fine-grained network measurements using software-defined networking and the high-speed programmable data plane. And prior to even joining the Princeton, as I told, he was in NIT Durgapur. He did his master's from CSE department in from IIT Kharagpur, and prominently he has done many research internships even in companies such as Netflix, ETH Zurich. Also, if I will introduce you to his research, he has done like work in prominent venues such as ACM Sitcom, ACM IMC, IEEE, ICMP, and the web conference that's formerly known as WWW. So without wasting any more time, I would like Satadal sir to continue with his talks. And today's talk will be regarding continuous in-network round-trip monitoring. Thank you.
So as I was just introduced, I am a previous student of NIT Durgapur, and I worked very closely with SN sir here, and my dear friend Vijay, who's traveled a long distance this morning to come see me. So I'm grateful to him for being here. The topic of my talk is continuous in-network round-trip time monitoring with Dart. This is joint work with Jun Kim and Jennifer Rexford from Princeton University. And the name of our group is Cabernet because Jennifer really likes red wine. So that was the first culture shock I got when I got to the US, because I don't think wine or alcohol is that celebrated in academic circles, at least in India. So just an anecdote there. A little bit about myself before I get into the meat of the talk. Oops. Sorry. So I entered NIT Durgapur for my B.Tech in 2009. Then I graduated and joined Oracle Financial Software in 2013, started my MS at IIT Kharagpur in 2016, and then started my PhD in Princeton in 2019. Some research highlights from my career so far. So I started working on delay-tolerant networks with SNSR and SSR back in, I think, 2011. Going forward, we built a nice team over here of 4. I still have this photo framed in my house, and Vijay is right next to me. He'll be speaking after me here. Following that, when I joined IIT Kharagpur, I worked on video streaming, traffic measurement, etc. So if you have questions regarding that later, please feel free to ask me. And then I did an internship at ETH Zurich right before starting my PhD at Princeton. And then during my PhD, I did an internship at Netflix. So these are just pointers for you to ask me questions later about this stuff. All right, so let me start with a little anecdote here, or rather a story here. We all know about Neil Armstrong, who set his foot on the moon. A lot of people worked on that project, but his name became the most famous kind of. These people here are kind of the Neil Armstrongs of the internet. The guy on the right, especially, he was the first one to send the first message on the internet that was successfully delivered. And the person to his left is actually, to the left of you, is actually his advisor, Leonard Kleinrock. So this was back in October 29, 1969, when these people were sitting in UCLA, and they were trying to send messages to Stanford Research Institute. And they tried to send login. Those were the 5 letters they typed in. And after L and O, their system crashed. So that was the very beginning of the internet. It started with a crash after LO. And 1 hour later, they were successful in sending that message through. And then that's where he writes that they were able to talk to SRI, Stanford Research Institute, host to host at 10:30 in the night. So that's where it all started. This network was called ARPANET. And then over time, the internet has come a very long way. So this is a map of the internet from 2003. It's not as dense, but by the time we were in 2021, you can see how many nodes have developed or shown up over the across the globe. So the internet is huge. The internet is very robust. It works for a lot of us, but we know that all is not well with the internet, right? So we see some news articles here about why is the internet slow, how network issues can cause Zoom problems or other apps, Microsoft Teams, whatever, and how there are attacks on the web every day, stealing a lot of important information or even cryptocurrency and so on. So let's take this particular example of cryptocurrency stealing and look into it a little bit to understand how this might work. I understand a lot of you here are not networking experts necessarily, so I will try to give you a bit of background, but feel free to stop me at any point and ask me questions if you do not understand something or if I can clarify something better. So the way this particular attack can work is by fooling BGP, which is the routing protocol of the internet. So how BGP generally works is that, say, there is a client at Princeton talking to the YouTube server, and then they announce each other's location, sort of. They actually announce the IP prefixes that are allocated to them. And so Princeton will say, hi, I'm here. YouTube will say, hi, I'm here. They all know, they both know each other's information. And then information flows across the globe to reach them. But this actually relies on trust for the most part. There is no checking by anybody for the most part of whether people claiming to be Princeton are actually Princeton and people claiming to be YouTube are actually YouTube. And so a malicious attacker can actually wrongly claim that, hey, I am YouTube, not that other guy there. And then Princeton can start talking to this guy as if that guy is YouTube. This actually happened in a famous attack, unintended attack, I must add, in 2009 when the Pakistani government tried to block YouTube within their country, but ended up blocking YouTube all over the globe. So one way to sort of launch this attack is to just stop all the YouTube traffic here. This is called a BGP hijack. So nothing goes to the actual YouTube server. Or the attacker can be really intelligent and it can say, hey, I know a better route to YouTube. So it can get all the traffic that is directed towards YouTube and then send across the traffic to YouTube as if nothing happened at all. And this way it knows stuff about whatever the client in Princeton is trying to do, but none of the two sides are any wiser about what is going on with their data. So why don't existing solutions work when detecting these kinds of attacks? So there is a resource, public key infrastructure, RPKI. I'm not going into the details, but essentially there is a cryptographic signing of a network when it announces a path. And this still has problems because the attacker can still lie by saying, I know a better path. So it only works when stopping hijacking attacks. And then BGP-SEC is another protocol that is used to validate the entire path information, but the border gateway routers of every network sort of need to support this. And we do not yet have widespread support for this kind of a protocol. So that's why existing solutions do not work. But it's actually very hard to fool the round trip time. What does that mean? So let's say you send data, or in this case, you send this robot across to some destination and you say, hey, deliver my package and come back with an acknowledgement. And this guy says, no problem. I came back within 5 minutes, right? And that's sort of what you expect, roughly. But say you give the same instruction and the robot comes back within 10 minutes and you know that you have forever taken 5 minutes. Why the hell does it take 10 minutes? So now you can have a sense of some sort of trouble happening on the way to the destination. And this is what we try to leverage in the rest of the talk. Yeah, that's the operator wondering why it took so long. So round trip time more formally is something like this. So let's say your browser is talking to the YouTube server, it sends a request, and the request reaches after T1 time. There is some processing delay for T2 time at the YouTube server, and then the response comes back in T3 time. And in this example, the round trip time would be from when the request started to when the response reached, which is T1 plus T2 plus T3. In general, RTT is actually a summation of 4 different things. I won't go into details, but very briefly, propagation delay would be one component, which is basically kind of like the speed of light distance between 2 points, or more like the distance on the wire. If there was no congestion, nothing, no problem at all, how much time it would take. Transmission time would be just putting bits on the wire. How much time does that take? Queuing delay would be how much the data has to stop in various switches and routers across the network because there is too much traffic. And then processing delay would be whatever time the end hosts take to process the data and run their algorithms on top of it and so on. Now, generally, the round trip time is measured at the transmission control protocol layer, the TCP layer. And I know a lot of you may not be very familiar with how this works, so I'll try to give you a brief about this as well. So let's dig into it. So let's see how TCP works very briefly, right? So TCP works by assuming that communication between two ends is via stream of bytes. So you have from byte 0 to byte n, and then these bytes are sent from host A, let's say Princeton, to host B, which is say YouTube in this case. And then these bytes flow across the internet over from host A to host B. And these bytes are actually not sent one by one. They are actually packaged into what we call TCP segments. And there are conditions for when these are sent, but essentially when a particular sized block is filled up, it is sent across to the other side. And these now TCP tries to provide reliable service, which means that it wants to know if it has sent something and if the other side has received it, then that reception has actually happened. It wants to have a proof that the other side has actually received it. So in order to enable that, what it does is it numbers these particular segments by something called the sequence number, which is basically nothing but the number of the first byte of that TCP segment that you can see over here. And then this goes across to the other end, and then they can have a reasonable sort of discussion about, the two hosts can have a reasonable discussion about what was sent and what was received and so on. And the ACK number is how the receiver then acknowledges what was received by it, right? So if host B acknowledges some TCP segment that was received by calculating the next sort of sequence number, which is sequence number of the first byte plus the length of the packet, right? So that would be the sort of the sequence number of the last byte. Then that would give it the acknowledgement number. It sends that back to host A, and that's how host A knows that the entire segment was received at the other end. So that was a very sort of quick overview of how TCP does things. There are a lot of other things to TCP, so feel free to ask me later. But I'll go into more details of how round trip time is actually measured for TCP. And in this case, let's take this example of a client and a server talking to each other. And TCP actually starts by way of a three-way handshake. So it sends a SYN packet across from the client to the server in this case to say, hey, I'm here and I want to start this connection with you. The server sends a SYN ACK back saying that, hey, I also want to participate in this communication. And the client then sends another ACK back saying, okay, all right, we all agree, let's start this communication. So that's the three-way handshake. And in this case, what you would measure here at the client, if you're measuring round trip times, you would measure the time difference between the SYN going and the SYN ACK coming back, and that would give you the handshake RTT. And then going forward, the client starts sending data over to the server, and these are data packets. We call them seek because of the fact that they are identified with sequence numbers, but essentially they are data packets. And then the ACK comes back from the other side, and this is what gives you per packet RTT. So if you compute the time difference, that gives you the per packet RTT. And you can keep doing this continuously over the lifetime of the connection, and this will keep giving you continuous per packet RTTs. Now, mind you that the communication can happen from the other end as well. It's not necessary that all packets go from client to server or all data packets go from client to server, but I show just one side of this for simplicity. So you keep doing this and you have continuous round trip time measurements for TCP. So these samples are created by matching the sequence numbers with the acknowledgement numbers. I was describing before how there is a logic to how these sequence numbers and acknowledgement numbers work. So they are matched and the timestamps are recorded and subtracted to get the RTTs. And then once the seek packet goes, the timestamp is recorded and then the client has to wait until that corresponding app comes back and then subtract that timestamp. That's the RTT essentially. Now, how can we leverage RT to combat attacks of the type that we showed before? So let's imagine a scenario where a client and a server are talking within the United States. And now there's an attacker in Europe who is trying to snoop in on this communication, right? And this is similar to the YouTube example we showed earlier. And let's say this guy wrongly claims that, hey, I am the client. And so in this case, what will happen is the data will actually first go from the server to the attacker because it thinks the client is located there. But the attacker is smart. It does not consume the data because then someone will figure out something is wrong, right? So it forwards the data back to the client and everything goes as if nothing ever happened. And it has been shown by previous works that these kinds of attacks are particularly hard to detect for reasons I have explained before. So all right. Why do these kinds of attacks? So I already cited the example of stealing cryptocurrency, but you could also imagine doing website fingerprinting. So for example, I want to know what Edward Snowden is doing, assuming he was in the US. So the government might want to snoop in on his communication, right? Might want to know what websites is he visiting, who is he talking to, and so on. So there are many reasons for why someone would want to do this. Now, notice here that the data actually was covering a very short distance when it was going directly from the client to the server or the server to the client. But in this case, it is actually traveling across the globe to come back to the client. And this is covering an extra distance of 15,000 kilometers, which amounts to at least 50 milliseconds more round trip time because of speed of light, right? We cannot do anything about that. And there is no way to hide this information. You can fool everyone, but you cannot really fool this. So can we use this? Wouldn't it be nice if we could use this information to detect and stop attacks of this nature? So what do we need to do this, right? And this is actually one example of what RTTs can do. It's not the case that RTTs can do only this, but this is, I think, a very compelling example of why RTTs might be important. Um, so nice to see Vibhas sir here after a long time. All right. So what do we need from a system that measures RTTs continuously? So first, what we need is this RTT measurement has to be real time. Because if we take a lot of time before detecting an attack, then the damage is already done, right? The risk increases per intercepted packet. We also need to measure this RTT continuously throughout the lifetime of a connection. So a connection can be very long. You can watch a YouTube video for hours on end. And if we only compute the RTT for the first packet, then that's not enough. So we have to keep measuring it every packet as we go along in that connection. And we have to measure the RTTs accurately, right? If we are wrong, then there could be false positives or false negatives. So false positives would be your system might claim, hey, there's an attack every few seconds. And the operator is now confused, like, what do I do about this? Nothing is working. I don't know when the actual attack is happening. And worse yet, if there's a false negative, the attack can happen and then you will never know. And then much later when the damage has been done, you'll come to know. So we want these features in whatever system we want to build to do continuous RTT monitoring or measurement. Now, what are the traditional RTT measurement techniques? So one way to do this is by doing active measurements, which means someone actively goes and pings some server. So you have all used this, I guess, whenever you've had trouble with your internet, you ping google.com or something. So ping, traceroute, hyperref, these are examples of tools that does this. There is a measurement host. It sends a probe to the server, and the server comes back with a response. And then the difference, the time difference, gives you the RTT. Now, this is good for characterizing the network. If you have multiple such measurement hosts across the globe, you can generate sort of a latency map of the internet. But when the user is actually watching something or doing something on the internet, this doesn't actually tell you what the user is experiencing by way of RTT, right? Because the measurement host is artificial. It's just some computer you have chosen. And the conditions will not be the same as the client's conditions would be. And also, this doesn't give you real-time and continuous RTT. You cannot keep pinging every second of the day. And even if you could, the network wouldn't support it. So this is not viable for this particular use case. The alternative is to do passive measurements. In this case, the client and the server keep communicating as usual. But what you do is you have a vantage point somewhere in between, right? You have some device in between that is actually trying to compute these RTTs, and that device computes the difference, the timestamp difference between the request and the response. And this is great for user experience RTTs because we see exactly what the client sees, especially if we are very close to the client. We're located within a few hops of the client. But how do we do real-time and continuous RTT? This doesn't really give us the answer for how do we do it real-time. And really, this depends on how we do passive measurements and where we do passive measurements. So I'm going to go into details of that. Now, more on passive RTT measurement. Where all can we do this, right? So we spoke about we need to solve two problems: where and how to do passive RTT measurements. Now, can we do it at the end host itself? Can you do it at your computer? Uh, no, right? Because then I would have to go to every person and install some special apparatus that does this. And that's just not scalable. And then everyone has to permit the operator or whoever is trying to do this to install a special software in your computer that's privacy invasive. You can never trust what this software hardware will do. So this is not possible. What one would rather do is measure at an aggregation point. So let's say NIT Durgapur has a network operator that is trying to manage the entire network, and they have this border gateway router through which all the traffic of NIT Durgapur flows, right? And that is the best point for them to actually do this RTT measurement, because then they can monitor RTTs for all the clients, right, across the across NIT Durgapur. Can we do it only for TCP handshake? I sort of alluded to this before, that there could be long connections, and studies have actually shown that only the handshake RTT is often not representative of actual RTTs between two entities when the connection has gone on for a long time. So no, we cannot only do handshake, we have to do it for per packet. And then can we do it in software? So how about we install a server and let all the packets go through that server and compute all the RTTs in that server? Now, why is this a problem? This is a problem because one way that people do this is by capturing what we call PCAP files, right? So some of you might be aware that we run TCP dump on a particular machine and we collect packet traces and then we analyze it offline. Now that clearly doesn't work because your attack will be done and after maybe one day you find out that an attack happened. And if you want to do it online, you want to do it live, then software is slow. Software is extremely slow in this case, and it has to work on GBPS or sometimes TBPS of data. And if you want to scale up the software to like scale up the servers that you have to support this kind of traffic rates, then it will be very expensive. You'll have to install, I don't know, a whole room of servers in that case. So the answer to this is actually high-speed programmable hardware that we need to leverage in order to do measurement like this. Now, what is the end goal? I'll come back to the point of high-speed programmable hardware because that's sort of in the meat of my talk. But let's look at the end goal here that we're trying to achieve. So we have the client and the server, and we have some switch or router in between. Right, and let's say this is near the campus or enterprise edge, as I was explaining. This is near the border gateway router of the NIT Durgapur campus, let's say. And let's assume, sort of fantasize that this is a high-speed programmable switch. It's not like the dumb switches that we have now. And this can actually be programmed to do various things. So now from the client, we have a stream of packets. So remember before that we talked about TCP segments, sometimes we call them packets interchangeably. Packet is sort of like a all-encompassing term referring to any package of network data, I would say. And so we have these stream of packets that goes through the switch and gets to the other end, to the server, by way of forwarding. This is very simple. This is what happens every day. But in addition to this, we parse some of the packet metadata, and then we do this RTT measurement within the switch itself. So we program the switch to do this additional fancy stuff. And then these stream of RTT samples are generated, and it goes to samples, and I can see that the RTT has clearly changed by an alarming amount. So stop the communication immediately because there seems to be an attack going on. So that you can program directly into the switch.
What is meant by packet metadata?
So we are referring to the packet headers here. I was trying to be abstract about it. So these are just the TCP headers or IP headers. All right. Oops. Okay, so I'll stop for a second and see if anyone else has questions so far. All right, let me go forward with this. So can a switch actually do this? And it wasn't until very recently, or well, a few years now actually, that the switches were equipped to do this, right? So this was thanks to the advent of SDN, or software-defined networking. I'm not going into details of that because it's not very relevant to the talk. But essentially, what it tried to do, what software-defined networking tried to do, was enable the actual owners of the network to program their own stuff on their switches. So earlier you would buy switches from Cisco or Juniper Networks or whoever, and they would tell you what to do, right? Like they would program your stuff for you, and you couldn't do anything on top of it. Think of your home routers, right? You can't do anything there. But SDN tried to bring programmability into the network, build programmability into the network. There are many facets. I won't go into the details, but programmable switches came out because of that effort. And so in traditional switches, let's say you want to say I have function A, B, and C. Sorry, the switch tells you that I have function A, B, and C, and I'll let you configure them. But if you want to do D, which is custom to you, then you cannot do it. Sorry, no, cannot do it. But programmable switches actually tell you that it has low-level building blocks, and you can actually program your own function on top of it. And if you want to do D, please go ahead. You're free to do it. So what do these switches look like? Essentially, they work on this concept of protocol-independent switch architecture, or PISA. And without going into a lot of detail, essentially it has sort of 4 features. It can let you customize how to parse bits in a packet. So you can tell it exactly which parts of the packet you need. So suppose you need only the source IP address and nothing else, you can just do that. Just pick that part. You can customize how to match and modify bits within the packet. So it lets you change bits. It lets you match on certain bits. So if the source IP is like this, then do this, something like that. You can customize what to read and write in memory. So it actually has memory in there where you can keep state. So if you want to remember, okay, over the last 50 RTTs, I saw this RTT trend, then you can actually see what the 51st sample does, right? Is it anomalous? Is it conformant to whatever you've seen so far, and so on. And then, sorry, the clicker is sometimes high latency. And then we can customize what to output. So you can actually, because you have modified the bits, you can actually go ahead and change the output. Absolutely. So that is what it lets you do. And then these hardware is actually at a store near you, as in you can go and buy this. These are expensive by our standards, but for operators, this is actually pretty affordable these days. So Intel Tofino is actually one of the main ones who are supporting a lot of research nowadays. Barefoot was the company that came up with this concept, but Intel acquired Barefoot later. So they're Intel Tofino now, but many of the universities now work directly with Intel Tofinos, as does Princeton. And then there's AMD and Pensando and so on, who also are in this. And here's a quote by Jen, my advisor, which I like to keep close to me, which is programmable switches are to networking what GPUs are to machine learning. So we know that machine learning has been revolutionized by the invention and sort of availability of GPUs, right? And programmable switches have done kind of the same thing to networking, where it has democratized networking and it has made it much more efficient. All right. And how do you program these switches? You program it using the language called P4, which was built specifically for this. It is an open source language, and you can go ahead and learn this via videos on YouTube and so on. Okay, but is it all like hunky-dory? No, right? So programmable hardware is severely constrained. Why? Because it has to be very, very efficient. It has to be really fast. And so I'm trying to, I'll try to go through some of the constraints really quickly. So let's say a packet comes in. These are the packet headers here shown in different colors. You have a parser using which you can actually parse out these headers. And you have a deparser on the other end where you can modify these headers, do whatever you want to, and then send it out on the other end, right? In between, what you have is a processing pipeline with a bunch of stages. And the number of stages are actually limited. So first, to show one stage, there is memory in each stage. And then there is computation in each stage. So there are ALUs in each stage, right? And the first sort of challenge that we have is that there is limited per stage branching or arithmetic. So you cannot actually do multiplication or division. You can only do summation and subtraction. So that's what you have to live with. And you can also not have too many nested ifs within this. It doesn't support that. Number two, sorry, the clicker is slowing me down. So number two is you can only have a fixed number of address lookups per stage. You cannot look up too many indices of a hash table, let's say. At the same time, you have to look up one or two at one time at best. And then you cannot actually go back after you have passed a stage. You cannot go back to a previous stage and look up memory from that stage. This is forbidden because there can be multiple packets in the pipeline at one point in time, and there will be inconsistencies if you allow that. So if you have to read something twice, you have to actually recirculate the packet. So there's a circuit within the switch that helps you recirculate the packet back to the front, and then you can do more processing on it. But obviously, it will slow you down, right? Because you're processing one packet twice. So it is decreasing your bandwidth. And the total register memory, the total amount of memory that you have in the switch is extremely limited. And then on top of that, you have many important functions to perform, not just one piece of code, right? So you have to be very efficient in how you write these applications so that they do not impede the implementation of other applications that are written on top of the switch. All right. So I'll come back to the end goal. I'll remind you of this picture, this thing that we wanted to achieve. So we have this high-speed programmable switch. We have the packets coming in. We want to measure RTT. And then something else does the analytics and mitigation. So we'll focus on the RTT measurement part now, specifically for TCP. So at this point, I'll ask if anybody has questions.
Will it be done per connection or will it be
Yes.
per
Yes.
connection?
This is done per connection.
That will be a huge, I mean, how will you accommodate checking of each of them and all?
Right.
How
Right.
feasible it is in a switch like this, where there can be several thousands and connections being monitored.
Right. So the answer to that essentially is that the
And another thing is, what happens if somebody tries to do something here malicious? I mean, the switch itself.
right. So to your first point, the switch is capable of handling TBPS traffic, right? So our solution has to work directly in the data plane. It cannot go to the control plane. So we have to do something very simple, which is also effective at the same time. So in one pass of the packet, and sometimes maybe two at best, we can actually collect these RTT samples. And that's where our work comes in, essentially. Devices that sort of very efficient data structure that lets you do that directly in the data plane. And it is true that malicious actors can target this. The problem isn't so much that someone can come and maliciously do something to say this switch that is within your server building or something, but it's more that someone can early act and fool you into recording smaller RTTs. That's sort of the major problem. And we are looking at ways to get around that as well. That is my current work right now. But in this work, we did not address that particular problem. We assumed that that attack was not happening. But you're right that that's a major problem. And the way we try to deal with that is actually trying to send counter packets through the malicious attacker to see if they actually are in the path trying to do something. So we spoof some packets and send it and see if they're being
But IPsec kind of things can work here.
To do the to stop from early attacks, early acts. Sorry. It can, yes. I think we were trying not to rely on any sort of separate layer of security protocols. But yeah, you're right. It could help there. All right. So how do we do? Sorry, I didn't check if anybody else had questions. Okay, cool. So how do we do continuous RTT monitoring at a programmable switch? We talked about the programmable switch. It is lying close to the client. It is monitoring all the clients on the network. And then essentially what happens is a SIG packet goes, the monitor, the switch actually computes the expected ACK number, which I alluded to before, which is the sequence number plus the length of the packet. And then when the acknowledgement comes back, it tries to check whether the acknowledgement number matches this expected ACK number. And this logic is actually like the records are actually kept in a hash table within the switch. And the key of the hash table is the flow ID and the expected ACK number. So this is per packet, right? This is unique to one packet. And then the timestamp, that's the value. So let's take an example here. So there is a source and a destination S to D, and the sequence number of this packet is 1000, and the packet length is 500, and it arrives at timestamp 200. So how this will be recorded is the 4 tuple will be stored, and the number 1500 will be stored because that is the expected ACK number, sequence number plus the packet length, and the timestamp is also stored 200. And then when the corresponding acknowledgement comes back at 300 milliseconds.
Don't talk. This is really bad. If you have something too serious, please go outside. And this is not at least a class that you need to be here to get attendance, right? So if you have voluntarily chosen to be here, and please try to be at least patient and try to listen. Otherwise, it distracts presenters' attention also. I'm sorry to interrupt you.
So by flow, essentially you have two endpoints, traffic between two endpoints.
Yes, and also one direction of that. Because if you change the source IP and destination IP, if you change the order, it will also change. Okay, so in this case, the RTT will be 300 minus 200, that's 100 milliseconds. And that's how, and that record is then deleted from the table to make space for other records essentially. Now, this is work that was previously done in our group, but it actually does not solve the problem entirely. There are many other problems on top of this that one has to handle. It's not this trivial to measure RTT. So TCP has many idiosyncrasies or peculiarities, and those are required for other functionality. But let's look at some of the idiosyncrasies that makes RTT monitoring hard, particularly. And these are per connection. So connection would be one or per flow even, right? So one sender and one receiver, just that pair. So the first one is TCP retransmission ambiguity. And what happens here is that, let's say the client has sent a packet and the packet gets lost. It has retransmitted that packet, right? And the measurement devices has actually seen both versions of that packet. So now when an ACK has come back, it doesn't know if the ACK is actually for the first version of the packet or for the second version of the packet. Because it could be that the packet was actually not dropped, it actually arrived very late at the receiver, and the receiver acted then, but the client was too impatient and sent the second version anyway, right? So this is one kind of ambiguity that we have to deal with. Then there is the reordering ambiguity. And here what happens is the packet is sent and an acknowledgement comes back. But let's say for the next two packets, they actually take different routes and they arrive at the receiver in a different order. And then what will happen is P3 in this case will be acknowledged first, will be do-packed actually, because okay, there are intricacies of TCP here. I'm not going to go into details, but essentially there's a feature in TCP where the server actually tells the client that something was not received by re-acking something it received earlier, right? So in this case, it is re-acking packet 1, P1. And then finally, when P2 arrives, that hole is filled. So everything is now good. And then the acknowledgement for packet 3 is now sent in response to packet 2 reaching. So this is wrong for the RTT device, right? Because it incorrectly matches packet 2 with acknowledgement 3 and sort of makes the wrong assumption that that is the correct RTT, whereas the actual RTT is perhaps lower. Then there can be multiple packets in flight. It could very well be that you have to record record state for a large number of packets in one go in your memory, and then your memory will be exhausted. And then there are packets that actually never receive ACKs. So TCP has this thing of cumulative acknowledgements where some of the packets will never receive an ACK, but a future packet will receive an ACK. And so what that means is these packets will keep living in the memory forever and never result in RTT samples. And so you have to have a way of sort of flushing them out of memory to make space for other packets, other future packets. I wouldn't worry so much about the details right now, but just know that there are challenges to this because of peculiarities of TCP. And then there are scalability issues on top of that. So there could be inactive flows, right? So there could be a lot of flows that start and then just stop with a lot of packets hanging, a lot of data packets hanging that have never gotten an acknowledgement. There could be thousands of connections. So this goes back to the question that SN sir was asking before. How does this scale to thousands of connections? And then there could be SYN flood attacks. So there could be attackers that actually send spoofed SYN packets. Sorry about that. Spoofed SYN packets, and then the acknowledgement goes, but there's nobody to respond to that. So now you're left hanging. You have collected data for that particular connection, but then those RTTs are useless, or those records just keep living in the memory forever. So we have to do this careful balancing act between the idiosyncrasies of TCP traffic and the scale of traffic as well, of course, and the limitations of the programmable switch. So we spoke about the limitations before, and we have to do all of this together. So that's really the core of the challenge that we tried to solve in this project. And how did we do that? So first, the way we wanted to design for correctness was to do this. So the challenges, again, in this context are the retransmission and reordering ambiguities, right? They are the issues, the idiosyncrasies of TCP that result in incorrect samples. And our solution to that was to store per flow state, to have some sort of an indication that it tells us when a retransmission or reordering has happened. And this way we can eliminate the erroneous RTT sampling. So how do we exactly do that? So let's imagine this is the flow sequence number space for one particular flow, of course. And there are packets or bits that have been, bytes rather, that have been already ACKed. And there are some that have been transmitted but not ACKed. These are packets in flight or bytes in flight. And then there is a part of the sequence space that is not seen yet. So these are increasing numbers, right? You go from byte 0 to byte whatever n. And we keep pointers to what is the maximum byte that has been ACKed so far, and what is the maximum byte transmitted so far. So we are trying to keep track of bytes in flight, essentially. And we call this the measurement range. So we are actually storing just two numbers, per flow at this point. It's called the measurement range. So under normal operation, this is all good. This is fine. But when we see a retransmission, the way we will see it is we will see a repeat of something we have seen before, right? So because we already know that some max byte has been transmitted, if we see it again, if we see some overlapping numbers again, then we know, hey, this is a retransmission. And the moment we see that, we do something, and I'll come to that later. But similar thing happens when an ACK packet is received, which for a packet which has already been ACKed before, right? So essentially, whenever there is a repetition of some order, so in this case, we know this is a reordering event. And in both cases, what we determine is that this range in between has been affected by retransmission or reordering, right? And we actually collapse this range. We say that it is unsafe to take any RTT samples during this
Something
time
like
period.
sliding window protocol, similar, I'm not saying.
There's, yeah.
Ideas like that, right?
Yes, like there are similarities in the ideas. Yes, that is
The
true.
window is maintained and
Right, but
flow control. I mean, again,
Right.
there may be differences, but the idea was.
yes, yes, of course. I mean, it is a sliding window. Yes, of course. The measurement range is a sliding window of valid bits,
Sliding
essentially.
window that we maintain in the link layer or maybe the transmission layer, so it is something similar to that.
Here it is a narrower window than actual slide.
Yes, yes, exactly.
But we monitor.
Yes, yes. Uh, Right. So in these cases, we collect no samples. And the measurement range now becomes the max byte affected to the max byte transmitted. And so if we combine the two definitions, we can actually come to this conclusion that the measurement range should be either the max byte act or affected, which one is the higher number, and the max byte transmitted. So that's our safe range, right? That's where we can keep collecting RTT samples without any errors. So far we have talked about errors, but there are scalability issues, right? It's like there are so many packets going all the time. So how do we deal with that? So how do we design for memory efficiency? That's the next question. Now, one thing to note here is that we are adding more information. Earlier, we were only keeping track of packet state. Now we are also additionally keeping flow state. Per flow, we need this measurement range. On top of that, we need the packet records. So how do we compensate for that? So this is how what we ended up designing. So let's say that a new packet comes in. We have this range tracker hash table in the beginning. And what it stores is essentially the measurement range that we just discussed, right? The flow and the measurement, the flow ID and the measurement range. And then the packet actually goes across to a packet tracker table. Something like this we saw before. It has 4 packet identifiers, the flow and the expected ACK number is the key, and the timestamp as the value. And then the RTT sample is generated. So this is sort of the data structure that we came up with. It's very simple. But notice here that there are 2 major problems with regards to scalability. One is there are cumulative ACKs, meaning many of the packets do not ever get ACKs. So we need a way to weed out those from time to time, right? But some RTTs can be really, really large. So if we just set a timer and say, okay, 1 second is over, get out of this hash table, that may not be enough. Some RTTs might be greater than 1 second. And then even if not, 1 second is just too high a time. So now, how do you decide the threshold? What is a good timer to keep, right? So we did not want to have that burden on us of deciding what a good number is for a timer. And so what we decided was that the best way to deal with this was whenever there was hash collision, whenever memory was already occupied and something else was trying to occupy that memory, we actually recirculate that entry to the front to check against the range tracker if that entry is still valid or not. If it is still valid, we reinsert it using a different hash function, essentially. But if it is already too late, if it is stale because the measurement range has moved forward, then we just drop it. And that makes space for new entries naturally. So this is sort of reactive, and we call this lazy recirculation with a second chance. Why is it lazy? Because we don't do anything unless there is a hash collision, unless there is memory pressure, right? There is competition for memory. But there is a second chance because if you kick something out, it still has a chance to live on because it might be that the actual RTT for that record is really, really large and it has to live on. So it gets to go back into the table and live there. The actual implementation actually has multi-staged tables. I'm not going into the details of that. So we are using sort of multiple, we are distributing the memory of these tables across multiple stages of the programmable switch to allow us to do more fine-tuned hashing, if you will. So how do you protect against SYN flooding attacks? We recognize one thing, that SYN flooding works only with handshake packets, right? It's the initiation of the connection. And so what if we do not store the handshake packets at all? Because we're collecting per packet RTTs anyway, we are not losing much by doing this, but we are protecting against SYN flooding by doing this little modification. And together, this system is called DART, which is short for data pin actionable round trip times. That's sort of our system that we came up with. And so the implementation is, there is a real implementation for the Tofino switch. We actually implemented this in our campus network, and we tested, verified everything. And there is like P4 code for this. It is open source. You can go ahead and take a look at it if you want. Now, how would we evaluate this, right? So let's go back to the attack example that we looked at in the beginning. We talked a lot about some BGP fooling attack, but how do we actually test that? Test our system against that. So there's this test bed called peering that is maintained by Columbia University and a bunch of other folks, which let you perform your own ethical interception attacks on the internet. So if you submit a project proposal to them, they will approve you in some time if they're convinced. And then you can actually launch these attacks on the real internet by yourselves. Of course, there are restrictions. You cannot disrupt anybody else's traffic. And so what we did was we launched such interception attacks, and we tested, we captured the data for that, and we tested our system against that. Now, how do we sort of detect, how did we do with detecting attacks in real time? So this was the example that we saw before. And as I said, the interception attack was launched using peering, and then the data was flowing between Princeton and Northeastern universities. These are within the US. And the adversary was in Amsterdam. I'm sorry for the graphic for Amsterdam. That's from the SIGCOM webpage because I was presenting there. I forgot to change that, but anyway. And so we actually see this really clean pattern that DART gives you in this case. So you can see that the RTT before the attack was launched around the 36th second. That's the x-axis. You can see that the RTTs were near 22, 23 milliseconds. And then just when this attack was launched, very quickly the RTT jumped, right? Because there was a huge deviation of the traffic. It went up to 110 or even closer to 120 milliseconds. And DART gives you the ability to see this clear pattern in real time and then work on it, like act on it. And so we implemented a very simple change point algorithm, change point detection algorithm within the switch itself that could detect this attack within 22 data packets and only within 2 seconds of the attack being launched. So you do not lose too many packets before you actually know that the attack has happened, and you stop it right then and there. But this was just the real sort of real world evaluation. You also did simulation based evaluation. So we had a campus packet trace that we collected for 15 minutes. It has millions of packets and thousands of connections. So 15 minutes, but for the entirety of the Princeton campus. So that was a lot of data. And we actually implemented DART in Python as well to explore its parameter space, essentially. And we collected RTT samples from this. And we compared the performance of DART against TCP trace. So TCP trace is an existing tool that works on PCAP files, packet traces, offline. And we sort of compared our accuracy against TCP trace. And our main takeaways, there are a lot of results in the paper, please feel free to look at it. But our main takeaways was that only using approximately 24% of the Tofino SRAM, we were able to collect up to 99% of the samples using just one stage. So I was talking about multi-staged hash tables before. So if we use just one stage, we are actually able to collect up to 99% of the samples with only 10% recirculations, which is quite okay by the established standards. And then if we increase the number of stages to 8, we can actually get almost all the samples, so close to 100% accuracy with just 16% recirculations. So it actually scales to the sort of Princeton production level traffic, at least in our experiments. So I'm towards the end now. What more can we do with Dart? So yeah, I already showed you that Dart is very effective against interception attacks, but we can do performance monitoring. So we can give people insights about network performance. We can tell people if there are problems in the network, then where they are. So it can act as a diagnostic tool. You can verify service level agreements. So if some operator comes and tells you, oh, I give you 100 milliseconds latency all the time, you can actually verify that. You can measure every RTT sample and then tell them, hey, something is not going right. And then you can improve congestion control. There is some work on how congestion control definitely relies on accurate RTT measurement. So this kind of a system would aid that most definitely. And I have a little bit of an anecdote here in this little plot. So we were comparing the RTTs of the wired network of Princeton with the wireless network of Princeton. And these were RTTs to YouTube and only the 90th percentile RTTs. And we actually saw that for the wireless part of the network, the within campus RTT was larger than the RTT outside the campus. So within the campus, the infrastructure was adding more latency than the infrastructure outside of the campus, which was going to some YouTube server, maybe in New York or something. And this wasn't known to anyone before we actually implemented this system. So that's really cool that we can do stuff like this with the system. We can do traffic engineering. So in real time, we can do things like selecting a replica of a CDN with low latency. So for example, in this case, say you have multiple clients and servers connected and you have these mappings and then something goes wrong, one server is congested, or the path to one server is congested, you can actually connect one client to a different server in real time, right? So in the previous use case, we were stopping attacks. In this use case, we can change the path in real time whenever the RTT becomes too large. We can improve video quality of experience. We can improve wireless hands-off and so on. And then I also want to point out that the design is actually quite generalizable. So we spoke about RTT measurement, but essentially what we did was we were joining two sides of the traffic, right? So there was one side which was going from the sender to the receiver, and another coming back. So if you have any use case where you want to join two sides of traffic, then this kind of a data structure would come in handy. And with that, I would like to conclude with just a refresher of what we discussed so far. So the first point I made was the internet is far from perfect. Round trip time is a key indicator of trouble, right? We spoke about how RTT monitoring needs to be passive, continuous, and real time. We spoke about how high-speed programmable switches, which are available now, have come to our rescue. In this case, we spoke about the fact that RTT monitoring for TCP can be challenging due to the, I call it vagaries, but idiosyncrasies, peculiarities of TCP traffic. And then Dart came in and it devised an intelligent data structure to perform this sort of balancing act between the two sides. And then we were able to stop a BGP interception attack in less than 2 seconds using Dart. And we also spoke about how this can actually help operators in taking control of their network, right? So do more with traffic engineering in their network, improving video QoE, and so on. And with that, I would like to conclude the talk. Thank you so much.